So now we're moving on to how intermolecular forces determine physical properties in liquids. And we'll get to solids later on in the unit, but we're mainly going to focus on how IMFs affect our liquid properties. So we're going to talk about melting point, boiling point, viscosity, surface tension, and vapor pressure. One of the properties of a liquid is that they have high density compared to gas molecules, and they've got a high density because they've got a compactness of molecules. Gas molecules are much more spread apart, and liquid molecules are much closer together. Liquid molecules are incompressible, and they also have the ability to diffuse due to fluidity. And just a reminder that when we talk about diffusion, we're talking about that things can move from a high to low concentration. Viscosity is the resistance of a liquid to flow. Viscosity is high if molecules do not move past each other easily. The stronger the intermolecular force, the higher the viscosity of the liquid. So if I'm talking about the intermolecular forces and viscous liquids, honey, syrup, and molasses are all really good examples of viscous liquids because they do not slide past each other very easily. If I wanted the intermolecular forces of those molecules to be weaker, I would increase the temperature. Whenever I increase the temperature on something, I've got the ability to break some of those intermolecular force attractions and allow those molecules to move past each other more easily. So because of the increased kinetic energy, those molecules can overcome those attractive forces. Anytime you see the word attractive forces, please be thinking about the 4 intermolecular forces that we have studied. So we're talking about overcoming those forces. Viscosity is also affected by molecular chain length and physical entanglement. So the longer the chain, the larger the molecule. And if it's got a very long molecule chain, then those molecules can actually get entangled in one another, which is why they wouldn't flow past each other as well. But for the most part, when we talk about viscous liquids, we want to talk about how we understand that they're not going to flow past each other because of high intermolecular forces. Surface tension is another property that's affected by intermolecular forces, and that's just a force that tends to pull adjacent parts of a liquid's surface together, thereby decreasing the surface area to the smallest possible size. And this varies from liquid to liquid. So if you've got a liquid with high intermolecular forces, it's going to have a lot of surface tension, so ST is just surface tension. If it's got low intermolecular forces, it's got low surface tension, or little surface tension. So another liquid property is capillary action, and that's just the attraction of the surface of a liquid to the surface of a solid. And remember, when we talk about capillary action, the best example of capillary action is how plants get water up the xylem. Remember, the xylem is how plants transfer water, and the phloem is how plants transfer food. And so plants are going to wick water up the xylem. Water will stick to itself, and water will also stick to the sides of the wall of the xylem. And we'll talk about, that's essentially adhesion and cohesion, and we'll talk about that in just a minute. So surface tension is the energy required to increase the surface area of a liquid. For a given number of liquid molecules, the highest surface area is to pull them all in a row, and the lowest surface area is to have them in a sphere. And so if you've got stronger intermolecular forces in liquids that have higher surface tensions, it's going to look something like this. So this would actually be a very good example of water, and this would actually be a very good example of something like acetone, or really anything with lower intermolecular forces. It's not going to stick to itself, so it wouldn't form the water bubble like we see a lot of times. Essentially, surface tension and intermolecular forces, as we've talked about before, are pretty much why skipper bugs can walk on water, because they're not heavy enough to break those intermolecular forces between water. They're not heavy enough to break that surface tension in the water. Here's another example of surface tension. Mercury has very high surface tension, which is why it used to be used in thermometers, because it would bubble up and over, and we would be able to see at what temperature it was because it didn't concave in. It was convex. Obviously we don't use mercury anymore for those because it's dangerous, and if thermometers break, then there would be a mercury spill. So cohesive forces, just a reminder, these are a measure of how well molecules stick to each other. So cohesion in water is just how well molecules stick to another water molecule. And then adhesive forces are a measure of how well molecules stick to other molecules. So essentially water to the side of a container or water to the xylem in a plant so that it can kind of wick its way up and get to the leaves so that photosynthesis can happen. If adhesive forces are greater than cohesive forces, then the molecules will maximize the surface tension. So the maximum adhesive interactions will be had. And this actually helps us determine the direction of the meniscus. And so if we can look at different meniscuses and see and be able to predict adhesive and cohesive forces and which one is greater. So if adhesion is greater than cohesion, the meniscus will look like this. So hopefully you're thinking, okay, in water, obviously adhesion is greater than cohesion. If cohesion is greater than adhesion, then the meniscus will look like this. And that's an example of when we used mercury in thermometers, where it would kind of bubble up like that. Capillary action is simply the result of adhesive forces. And an example of adhesive forces in another area of science is paper chromatography, which is just a separation technique based on differences in adhesive forces. So just another picture here, an example, nonpolar liquid mercury forms a convex meniscus in a glass tube, whereas polar water forms a concave meniscus. And so we can also make some predictions based on the molecule polarity if adhesive forces will be greater than cohesive forces. So there's looking at some of our liquid properties.